I think do you have anybody lined up for the next week or two?
I sent them an email, and, yeah.
Well, I think I want to go through the ideas of the second law of complexity, so I'll probably.
Oh, okay.
I've got 2 weeks. And not hurry it. I think it's important, the second law of complexity. I think it encapsulates some of the laws of gravity, maybe all of the laws of gravity. It plays a role which I think is a generalization of the role of the second law of thermodynamics in gravity. An example of the second law of thermodynamics in gravity is the fact that horizons grow. That's also something that you can derive from general relativity. So it's a parallel between thermodynamics and dynamics of gravity. In fact, it says something a little bit surprising. It says that certain laws, dynamical laws of gravity, are really statistical in character. Now, of course, these are the sorts of things that Ed Jacobson and others have been saying. I think it's probably a special case of something wider that includes the second law of complexity. That is the second law of complexity, the tendency for complexity to increase. And that includes such phenomena as the growth of the interior of black holes, not just the growth of horizons, but the growth of the of wormholes. I think it also underlies gravitational attraction for reasons I think we talked about last time. And just ordinary gravitational attraction may be a manifestation, I suppose you could say, of the growth of operators, but the growth of operators is a manifestation of the growth of complexity, and so my guess is a lot of gravity is just the tendency for complexity to increase. That's why I think it's important. I could be wrong. All right, let's, what I want to do today is to start trying to give a somewhat technical, not terribly technical, I don't know anything terribly technical about this subject, but somewhat technical about the geometry of complexity. The ideas that were originally pioneered by Michael Nielsen, we don't think he got it exactly right, but the basic idea, I think, is sound. But the real goal is to construct what you might call a statistical mechanics or even a thermodynamics of complexity. Complexity is an incredibly hard subject. It is, well, let's just say, it's very difficult, both in its guise as what computer scientists do, which study complexity classes, but also in proving things and making sure that you understand the evolution of complexity. It's very, very hard, and reasons we'll describe. But it might be a lot easier on the average. Sometimes things are easier on the average. So you have a large ensemble of, for example, you have a large ensemble of Hamiltonians. None of them you may be able to prove the complexity growth behave in a certain way, but you may be able to argue that on the average, almost all of them go that way. Now, I'm far from being able to do that, but you want to set in place some basic statistical ideas, a statistical mechanics and a thermodynamics of complexity, if you like, where complexity would play a role parallel to entropy. The growth of complexity would play a role parallel to the growth of entropy. The equilibrium that happens when complexity reaches its maximum and sits there for a very, very long time would be analogous to thermal equilibrium. And to see if we can't understand, I don't know why this subject has never been, I don't know why this isn't the standard subject of complexity theory, the parallel between complexity and thermodynamics. I must be missing something, or they're missing something. It seems obvious to me that we want to understand. Now, I think it's more or less obvious that if you start a system in a relatively low complexity state, what's it going to do next? Well,
become more complex,
Why?
because.
This is a test.
Yeah,
This is a test.
Because time evolution involves adding operators.
Well, okay, this is true. I'll say that, I'm gonna say it a way that I think is a more general way. There are more states of high complexity than low complexity. Just as there are more configurations of a classical dynamical system, more states of high entropy than low entropy. So, and that's all it takes. In particular, if the number of states of a given complexity grows exponential with complexity, then you really have a situation which is parallel, very parallel to thermodynamics, where the number of states with a given entropy grows exponentially with the entropy. So if one can establish that the number of states with a given complexity grows exponentially, then there's a very strong reason to believe that, there would be a statistical mechanics and a thermodynamics of complexity, and a useful, perhaps a useful tool in averaging problems, not focusing on a particular Hamiltonian, but asking averages over ensembles of Hamiltonians. Now that should ring a bell. SYK is a theory where you average over Hamiltonians. And so a natural place to try to use these ideas, I think, would be in SYK. And we'll talk a little bit about that. But let me just very quickly refresh your minds about a point that I've discussed probably so many times that you're probably sick of it, but nevertheless, let's mention it again. If I were to plot the growth of complexity is time, this is complexity. How do I expect it to behave? I expect it at time t equals, assuming that we start with some very low complexity state. We expect it to start small. Why? Because it started small. And then to grow, because it's the only thing to do. And we've argued in the past that it grows linearly. This, incidentally, is something that is also true of entropy. That entropy, when you start far out of thermal equilibrium at low entropy, the entropy grows linearly with an exponent which is called, the exponent is called Kolmogorov-Sinai entropy, which is actually a rate of growth. And it has a particular significance. We're talking about classical statistical mechanics now. Classical statistical mechanics, there's a linear growth, basically until, very close, until the entropy, I'm now talking about entropy, until the entropy reaches its maximum value, the maximum value being the thermal equilibrium value, and then it turns over very long time scales, exponentially long time scales. It can fluctuate, even go back to zero, and go up again, and those are Poincare recurrences. Okay. The upshot of the discussion that we had about complexity and following the same pattern, the upshot of it, well, let me just remind you, thermalization takes place fairly rapidly for a system of a large number of degrees of freedom. It certainly doesn't take more than a polynomial time in the number of degrees of freedom to reach thermal equilibrium. Otherwise, we would never see anything like thermal equilibrium. And it takes a single exponential amount of time to do a Poincare recurrence, whereas the complexity, we expect the complexity to increase for an exponential time, exponential in the entropy, or in the number of degrees of freedom, and then sit around at the top like this in some sort of equilibrium until quantum Poincare recurrences happen, and that's an e to the e to the s. So compared to the growth of entropy for a system of a certain size, for the same size system, the complexity seems to be an exponentially larger thing that exponentially grows for an exponentially longer time to an exponentially larger magnitude. The particular largest complexity is of order 2 to the number of degrees of freedom rather than number of degrees of freedom. All right, that's the kind of thing we can hope to explain. Well, we can hope to explain it, but what we need to explain, what we need to understand, is why the complexity behaves like the entropy. Why the complexity behaves like the entropy, not of a system of, let's say, the number of degrees of freedom. For some reason, I started using K for the number of degrees of freedom rather than N. It was a long time ago when people still talked about too many kinds of N's. And gauge group N's, supersymmetric N's, and so forth and so on. They gave up on that and started to call it K. So K is a number of qubits or a number of fundamental degrees of freedom. For a system of K degrees of freedom, let's say K classical degrees of freedom for a moment, the maximum entropy would be of order K. The maximum complexity of a K qubit system would be of order e to the K. And so again, everything is exponentially larger. The question is, if there is a statistical mechanics of complexity, what is the system for which it is the statistical mechanics? Whatever it is, it must have not K degrees of freedom, but basically 2 to the K degrees of freedom, or at least exponentially many degrees of freedom. There must be some underlying system, or some analog system, was the right term. I think we called it an auxiliary system, classical in nature, which instead of having K degrees of freedom, has 2 to the K degrees of freedom. If we can find that system, understand what it is, and understand why its entropy is the complexity of the corresponding quantum system, then we're kind of in business. And that's where we're going to try to make some progress. Now, this is not really a class, it's a seminar. These things are not fully accomplished. There's a lot of really interesting problems, mathematics problems, physics problems here. And I'd be happy to talk to anybody who wants to get into it. Thus far, this subject, I think, is kind of virginal, is the word, untapped, unexplored. Okay. Just as a matter of convention, I will sometimes use a time, T, and T, when it comes to black holes, T is Schwarzschild time. Or boundary time in a holographic setup, Schwarzschild time. I will also use tau, where tau is Ringler time, and the relation between them is tau is equal to, I can never remember, the 2 pi over beta going in the numerator to the denominator. Beta pi, where beta is the, and in many ways, this is a more convenient variable for many, many purposes, particularly for this purpose, but they only differ by a factor of 2 pi over beta, and beta is, it's polynomial in the number of degrees of freedom, so there's no exponentials around coming from this change of time variable. Okay, the other thing is, we're going to pretend that a black hole can be described as a K qubit system with K equal to the entropy. Okay, or order to entropy. Now this is a kind of matter of faith, that you can always describe systems by a number of degrees of freedom that's no bigger than the entropy. That any other degrees of freedom that the system might have are irrelevant. They're frozen. They're too frozen out of the system. But if we really want to make this idea more precise, then the natural and nice place to do it is in SYK, where you really do describe the system, which looks like a black hole, by a system of qubits, where the number of qubits is of order the entropy. So there's a very concrete example of it. And, you might want to fall back on that example if you want to be precise. Okay, so let me just expand on this for a moment.
So Lenny, with SYK there is a there's a linear factor at the front, right?
Linear what?
Like it's not the entropy that you get, sorry, the entropy is not n, it's like something proportional to n, right? If the small
Yeah, but it's never
yeah.
very far from n. It goes from the high temperature limit, where it's n log 2.
Yeah.
Actually, it's n, in that case, n is half the number
yeah.
of qubits. N log 2 to the low temperature limit, where it's 0.21 in or something like that. So it goes from 0.21 to 0.35. So apart from that factor of 2, from 2 point, almost ratio of 0.21 to 0.35, it's less than a factor of 2, yeah, between high temperatures and low temperatures. So over the whole range, you're never very far from the situation where the entropy is the number of qubits. Okay, so let me just make some more remarks, just to set the context. I've argued and given you arguments why the time rate of change of the complexity, now ordinary time, in this region where the complexity is small and increasing, why that is equal to the entropy of the system times the times the temperature. Entropy of the system just tells you how big the system is, how many degrees of freedom it has. Temperature is the unit of rate, is a rate, and this seems to work out very nicely in a number of contexts. In particular, it describes, it is equivalent, not equivalent to, but it is manifested in both the complexity volume idea, where the complexity is the volume of a wormhole, and also in the complexity action principle, which I'll assume you know, but if not. The two of them, both, the main context of the two of them is this. And I just want to point out that if you write this in terms of Rindler, which we've done before, but I just to remind that this just becomes, I'll call it C dot, and dot refers to Rindler time. I find it the more useful time coordinate when thinking about these questions of computation and so forth. And that would just be S. Now there may be some, beta is inverse temperature, pi is equal to 2 is equal to 1, and this formula becomes equal to C dot equals S, which is another way of saying that the rate of complexity growth, complexity is measured in gates. That's a unit of complexity. This says, roughly speaking, that there's one gate per Rindler time per degree of freedom. Each degree of freedom is involved in one gate per Rindler time. That's why I think it is the natural clock for thinking about a computer. You have a question?
Sort of. So this formula makes, it doesn't make sense that the reason why the time rate of change of complexity is constant is because we've already reached thermal equilibrium, entropy is maximal.
Well, that happened way down here.
Yeah, and then complexity grows linearly because, entropy is maximized. But then it stops growing, so we're at zero entropy?
No, it doesn't, it grows. It grows linearly for reasons that we'll see when we think about the statistical mechanics of it. But it grows linearly simply because if you think of a Hamiltonian circuit or a Hamiltonian system as evolving, as being like a quantum computer evolving, where the Hamiltonian evolution is just laid down as a series of gates, then the number of gates is proportional to the time, that's all.
Yeah, no, I get that. I'm really asking about the top of the late
Oh, the
time
top, the
behavior
top, the top,
in light
yeah.
of this equation, C dot equals S.
Oh, no, this is only meant to.
This is
apply-
only when it's growing.
Yeah.
This shouldn't be
Yeah.
true on top.
Yeah.
Okay.
Okay, so, we'll talk about black holes for a minute. Almost all states are up here.
Yes.
That's like saying that almost all states have maximal entropy, classical configurations. Almost all states are up here. But on the other hand, all states, it takes exponential time to get to these if you start with something simple. So everything in nature is in here. Everything that hasn't taken an exponential time.
Yeah, I understand. I was just
Yeah.
confused because I thought this meant S equals
Right.
0 when it's steady, but
Yeah.
it doesn't
No,
apply
no,
there.
no,
So
no,
good.
no, that's right,
Great.
no. No, this is specifically about that early growth.
Sorry, how about the very small times?
Oh, very small time. Time, let's say, smaller than.
Than entropy saturation. So
Yeah,
you know that the
um,
complexity goes linearly, but
yeah.
your formula, because entropy is smaller. Very small. So
Yeah,
you-
yeah, good. Okay, so a black hole, when a black hole is formed, it very quickly comes to thermal equilibrium.
But for time before that, this formula is probably not valid.
This is times less than the
Scramble.
Schwarzschild, less than the Schwarzschild transit time. Less than a millisecond for a solar mass black hole. Thermalization takes place extremely quickly. And yeah, that's right. This is between the early time while the system is experiencing its growth to equilibrium, to then until exponential times. Yeah. Now, these things are, as I said, not theorems, and nobody's going to prove this. I've been told, in no uncertain terms by my friends who are complexity experts, that nobody is going to prove this. And I believe it. I think it's potentially possible that we will prove it, or at least give a significant argument for it on the average. On the average, averaged, let's say in the sense of SYK. This I think is possible, and that's worth exploring. We could also, the same thing incidentally happens for random circuits. What are they called? Brownian circuits? Brownian circuits where you don't have a Hamiltonian, but you just have random sequences or random layers of gates. This also happens. In fact, probably the whole thing is pretty similar. So that can also be explored. Okay, the other thing about complexity, the other thing about what I've been calling complexity, our goal is going to be to try to find a better concept of complexity, a mathematical definition, a geometric definition. But one of the things, and an important thing I think to keep to remember, is the switchback effect. The switchback effect is,
What happens if the phantom energy is aggregation into black hole?
what happens if what? If,
Phantom energy, for example, dark energy of the universe,
oh, I don't know.
aggregation into black hole and black hole mass is decreasing.
Mhm.
At times, if black hole mass is decreasing, entropy is also decrease. So,
Decrease?
yes.
Why? I don't understand why it's decreasing, the entropy. If things are falling into the black hole, the entropy is increasing.
But if mass is decreasing too much,
Why is it decreasing?
because of the phantom energy aggregation. And
I
before
don't know,
that,
let this me later, I'm not sure what okay. Good. The switchback effect is an important sort of diagnostic. It's a feature of quantum circuits, and I'll just remind you very quickly what it is. If we have a simple operator, let's say a 1-qubit operator or something analogous to that, let's call it W. We use W because it's the same notation that Steve Schenker and Douglas Stanford introduced when thinking about shock waves. The kind of operator that you would apply long in the past to create a shock wave, but now just imagining you could apply it at some ordinary, at some other time, then the so-called precursor operator is just the evolution of this by time t, or time tau. Oh, I didn't finish, yeah, we did. Yeah, that's right. The complexity, the rate of complexity increase is just proportional to the entropy when expressed in terms of Rindler. So here I'll use the Rindler time. The complexity of this operator is of order, let's say, k times tau. The complexity of this one is also of order k times tau. And the complexity of this operator is order 1. You might think if you multiply them together, the total complexity, the total number of gates that it would take to make it, you might write down twice k plus 1. The 1 is not important, I'm not going to bother with it. Twice k tau times 1 times twice k tau. You might. In fact, the main thing you could say with rigor is that it is less than or equal to this, because this is by taking the gates from here, compounding them with the gates from here, and the gates from here, you can certainly make this operator. So you can certainly do it with 2kt gates, but you can do it with fewer, and that's t minus t star, tau minus tau star, scrambling time. This is called switchback effect. And it's an important diagnostic that you don't want to lose along the way, that you can short circuit, because it's the thing that tells you whatever quantity you're talking about should satisfy this on the grounds that complexity is by definition the minimum number of gates that it takes to make something, not the number of gates that you might have introduced to it, the minimum. So this is a kind of test of that. And we want whatever our definition of complexity to be to satisfy that. Okay. That's just a quick review. The quantum system, the kind of quantum systems we're going to describe are the kinds which are likely to describe black holes.
So is there a formula for tau less than tau star?
Yeah, there is. It's the epidemic function.
Okay. Oh, yeah.
Yeah. And, yeah, the exponent, yeah, I do. Tau star. It exponentially increases. It exponentially increases with the famous Lyapunov exponent, but the exponent is 1 in tau units. Tau units, the Lyapunov exponent is just 1. So it increases just simple exponentially. Eventually it has to get up to k, because that's how it has to get. And then it jumps up, and then it continues to grow linearly. That's the way it would behave. Now this is not the complexity of the original system I started with. This is the complexity of the precursor. Complexity of the precursor, and the reason for the switchback is because if there's only one gate here, if there were no gates here, you would just cancel all the gates from here and here, and you would get no complexity growth, no complexity at all. This one extra gate here doesn't prevent you from canceling out most of the gates in here, but as the epidemic spreads, eventually you can't do that, and that's just this switchback. Okay. So we've talked about this at length. All right, the quantum system that we're interested in. I could simplify this whole discussion about what the quantum system is, but just saying SYK. But we could I think we can reasonably study somewhat more general things. The main ingredient is that they're k-local, not capital K local, but small k local, with small k much smaller than large k. Examples being matrix theory, Yang-Mills theory at a single point, in a single cell, k-local, a system of qubits coupled all-to-all couplings, k-local but not spatially local, generic. generic, and we'll decide what generic means. All possible couplings, but K local, no bigger than K. In SYK, in SYK, K is called Q. All right? K is called Q in SYK. SYK. So we're interested in Hamiltonians of the form sum over, I don't know, I, J, K, L, psi I, psi j, psi k, psi l, j, I, J, K, L. And we'll be interested in ensembles, statistical ensembles, in exactly the same way that SYK is interested in ensembles. For example, Gaussian ensembles of J with a certain spread, with a certain width, and that's the basic parameter of the theory. We could also be doing equals, another possibility. For example, sum of I and J with simple Pauli matrices. This is the ith Pauli matrix, meaning the ith qubit. This is the 8th component of the Pauli matrix, 1, 2, and 3. So you see the J, B, with then a bunch of J's, depending on I and J and A and B. Same kind of thing, some statistical assumption, likely to be Gaussian description of the J's here. Those are the kind of systems I'll be interested in. These are the systems which we believe are fast scramblers. Fast scramblers mean that the scrambling time here, tau star, is equal to logarithm of S or logarithm of K. That's the meaning of a fast scrambler. And as you know, this is the character of the scrambling that happens basically in all black holes.
Is it clear if these systems have maximal Lyapunov exponent?
Is it clear?
Like in SYK, there is,
Yeah.
you can calculate it, and the Lyapunov exponent is 2 pi over beta, but
Yeah.
is it clear that here it will also be the case?
Oh, in this case here, no, it's not clear at all. No. No, it's definitely not clear. It's a question.
Yeah.
Right. I think this is not such a great system for studying at low temperature because it has this spin glass phase, which is a nuisance. But I don't know how bad that is. Okay. We could write the Hamiltonian more generally. Let's take this case here, but it would also apply here. We could write the Hamiltonian in a general form. Let's say sum over J sub I, I'll tell you what I is in a minute, times sigma sub I, where sigma sub I is any of the elements of a Pauli algebra. That means things with one Pauli matrix from one qubit, any one of the qubits, product of 2 Pauli matrices from 2 different qubits, product of 3 of them, product of 4 of them. How many elements of the Pauli algebra are there? The answer is 4 to the k. You can work that out. 4 to the k, I ranges, not I and j, some I. Some I, the I, j, the I, and sigma I, but with a restriction that the only sigmas that appear here are the ones which are k-local. So I could write it more generally like this one. I don't every time want to write down J, I, J, K, or whatever. Just a thing like this, and remember what the restrictions of k-locality are on the coefficients J. Those which are k-local, we might distribute Gaussianly. The rest just set equal to 0. I think it's also possible to have some more smooth, gradual turn-off of the coefficients. And that might be interesting. But, I will use this notation, capital I here, for the 4 to the k elements of the algebra. One of the elements is just a unit matrix, so there's 4 to the k minus 1 non-trivial sigmas here. 4 to the k. Very high dimensional space. Okay. Now, talk about the Rindler Hamiltonian. The Rindler Hamiltonian, if the ordinary Hamiltonian, Schwarzschild Hamiltonian, is by definition minus I d by dt, I think you know what I mean by that. That's what we usually call the Hamiltonian conjugate to the time here. We can also consider minus I d by d tau. It's just gonna be a multiple of this h here with the beta over 2 pi appearing someplace or other. H Rindler is equal to this, which is beta over 2 pi, beta over 2 pi, I think, times H Schwarzschild. Now, do I have that right or not? Beta over 2 pi, yes, I think it's beta over 2 pi, not 2 pi over beta. Okay. Now, for a Schwarzschild black hole, what is H Schwarzschild? It's the mass. So, we can think of this then as the mass. And the Rindler energy, this is not the Hamiltonian, this is the eigenvalue, or this is the energy associated with the Hamiltonian. We can write that the Rindler energy is proportional to beta over pi times the mass. For Schwarzschild type black holes, beta is essentially equal to the Schwarzschild radius. Beta is a length, it's an inverse temperature, it's a length, and it is equal to the Schwarzschild radius. The mass is what? This is radius, and mass is radius times divided by g, huh? I'm thinking 4-dimensionally, but this works in any dimension, if we're right. E Rindler, the energy of a Rindler, is the Schwarzschild radius squared over the Newton constant, which is also called the entropy, which in our notation is just K. So the Rindler energy, its magnitude, its value for a black hole, is simply the entropy itself. Okay. Entropy is energy for Rindler. That's a fairly general fact. But that's it's general. Completely general?
You're sort of saying the energy is ST, right?
Hmm?
It's similar saying the energy is S times T.
Yeah, it's also saying the energy is S times T. It's really dE equals TdS, but they always scale the same way.
So it's true in ADS.
Hmm?
Also true in ADS.
Okay.
True in ADS, it's not true in the extreme black holes.
Yeah, but a generalization of this is true. So charged black holes are a thing of their own, which are also interesting. But okay, this is here as two facts. Where I'm going with this now is I want to normalize the J's. I want to tell you how big the J's should be chosen in order that you're mimicking a black hole. Okay. So first of all, we have Rindler energy is equal to S. What about delta E for a black hole? The fluctuation in the energy. Well, I'll tell you now, for the Rindler, I'm talking about the Rindler energy itself. The fluctuation in the Rindler energy is just the square root of S. This is true for all electrically neutral black holes. It may be true for all black holes. I have to think about that. Any number of dimensions, whatever, up to factors of order 1. The uncertainty in the Rindler energy is of order square root of S. This is not too surprising. Well, it is a little bit surprising. What it's kind of saying is that the energy is additive over the number of degrees of freedom with independent fluctuations. With independent fluctuations. That's the kind of thing which would give you this kind of behavior. On the other hand, the Hamiltonian is not local. It is not the case that, that things only interact with a small number of other things. Everybody interacts with everybody else. So this is a little bit of a surprise. Why should the fluctuation in the energy behave as though there were separate degrees of freedom, not interacting very much? Everybody's interacting with everybody else. Well, I don't really know, but I know how to impose it. Oh, this, as I said, where does this come from? Where do I get this from? I get this from black holes by calculating the specific heat. You calculate the specific heat, which just means the rate of change of energy with respect to temperature. And specific heat is a measure of fluctuation of energy, standard thermodynamic relationship. Specific heat is proportional to the fluctuation of the energy, and this is generally true.
So just because these degrees of freedom are interacting, I would still have the intuition that they're independently randomly distributed. Right? The interaction, they're still independent and random.
So,
Unless there's, yeah, I guess I would expect that anyway.
We can talk more about why this is true, but let me just tell you what it imposes.
Sorry, but it's one quick question. So this just follows from the scaling of the entropy with the temperature, right?
Yeah.
So it's true
Yeah.
for any
Yeah,
CFD.
but, right. You calculate the temperature by looking at the surface gravity, you calculate the entropy by looking at the area, and so you can do it geometrically also.
Okay, but in the boundary, you can just think like the.
Yeah, do it from the boundary
the-
side, you can do it from the geometry side of the black hole. You don't even have to have a boundary, it could be an empty flat space. This will always be true. So, good, okay, so let's go back to the Hamiltonian. I'll assume I'm talking about the Ridley Hamiltonian now. And write, for example, that it is of the form J_I_J_K_L. Sorry, I, sorry, J, sorry, K, sorry, L. Or it could be the two qubit, just something K local or Q local with a definite number of, in this case, fermions in it. How do we normalize the J? We want to normalize the J so that the fluctuation in the energy is equal to the square root of S or the square root of K. And so let's see what that says. This is sum over all I, J, and K. The square of the Hamiltonian is just, let's call it J psi 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 times another J psi 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 psi. All right, now, let's work at infinite temperature. The work at finite temperature is more complicated, but the results, if you look at the last paper we wrote, you'll realize the results are basically the same. At infinite temperature, the way you calculate this is just to take a trace over the Hilbert space. Just trace everything. And what are you going to get? You're going to get, you're going to match when I here, if none of the si's here, let's for them, I, J, K, L. If they don't match, you get 0. If they all match here, and they all match here, you'll get something. You'll get 1 for each contraction, so to speak. But then there's the permutations of the way that you contract them. In any case, what you're going to get is J squared times K to what power? The 4th? Yeah. I can be any one of K. Whatever this is, J could be any one of K, K minus 1 to be exact. This could be any one of K minus 2, and this one could be any one of K minus 3. Basically, you're going to get, in this case here, something like K to the 4th, or really K to the Q. K to the Q, where Q is the Q of the SYK. And that we want to be equal to, this is the square of the fluctuation. Oh, I left out one thing. The way that I'm writing things here, the average energy is always 0. So in calculating the fluctuation of the energy, we just have to calculate the square of the energy. The average energy is 0 because the traces of Pauli matrices are 0 and so forth. But, the average energy is 0, but the ground state energy is negative. So the difference between ground state energy and so what should we set this equal to? We should set this equal to K. That's what black holes are telling us here. And so this becomes 1 minus Q. The average of J, the average magnitude of the coupling constants which appear here should satisfy this relationship here. That's a standard relation in SYK, but this is where it comes from. Or at least this is one place it comes from. For Q equals 2, this is just 1 over, what is it, 1 over square root of K? 1 over square root of K. Okay, so this is just normalization. It's important to get it right, but once you got it right, we may come back to it, but it's there. Okay, that's the quantum system I'm interested in. Any questions about the quantum system? And the point is that if you normalize the J's in the way that I did, all of this goes through, and you will find that the complexity grows as S times T. It'll be extensive. It'll grow as S times T, as opposed to S to some funny power. Okay, now, the classical auxiliary system, whose entropy is equal to the exponentially large number, whose entropy is equal to the complexity, here's what it almost certainly is. The wave function of a system, the quantum wave function of a system, is a function of time. Well, let's not do quantum wave functions, let's do unitary operators. Unitary operators. Incidentally, the unitary operators are kind of in one-to-one correspondence with the wave functions of pairs of systems that are maximally entangled. So I could be, when I'm speaking on U, I could be speaking at the time evolution of one system or the wave function of a maximally entangled pair of systems. Same thing. U evolves with time. It lives on some space. What's the space? The space is SU2 to the power K. Y2 to the power K. Well, the number of qubits is K. Dimensionality in the space of states is 2 to the K. And so we're talking about unitary operations on a huge space, SU2 to the K. Here's SU2 to the K. It's not a sphere. In fact, it's a complicated space. It is homogeneous. It has the following features. It's homogeneous. It is non-isotropic, but it's kind of locally isotropic, but it's non-isotropic. And it is bi-invariant. Anybody know what bi-invariant means?
It's the same at the left or on the right.
It's invariant under multiplication either by the left or by the right or both.
So your measure is bi-invariant.
Hmm?
Your measure is bi-invariant.
The metric itself is, the metric of the space.
Oh, metric is the
The usual metric. We'll come to what the usual metric is. The usual metric is bi-invariant. Yeah, the measure is also bi-invariant. But in particular, the metric of it. I'll write down the metric a little bit. Well, maybe I'll write it down right now. Its dimensionality is exponential. The main thing is that its dimensionality is exponential. So motion on this space is classical motion. It's not yet clear that it's got a Hamiltonian or an action or anything like that, but it's motion, it's classical motion on a space of exponentially large dimension. What I will argue,
Motion with respect to time, so you are
with respect to time, yeah. What I will argue is this is a dynamical system, and this is the dynamical system whose entropy is the complexity. Okay, so that seems... somewhat interesting. Let's write its metric. Now when I say its metric, I mean the bi-invariant, let me call it the standard metric. I don't know if it has a name.
Arm.
No, for CPN, it would be the Fubini-Studi metric. I don't know what that is, but it's easy to write. I think maybe just call it the bi-invariant metric. And there's only one bi-invariant metric up to a numerical multiple, left invariant, right invariant. Okay, so here it is. PL squared is, what we're talking about now is we have 2 points separated by a differential distance. So there's a little du here, separating 2 points. The metric is trace of du dagger du. Really simple. That's the bi-invariant metric. And you can see it's bi-invariant. Supposing I multiply u from the left by something, v, then I should multiply the u dagger from the left, I should multiply u back from the right, and then I can bring the u and the u dagger around, trace is cyclically invariant. This quantity is invariant. If you stick the u and the u of inverse in here, they also cancel out. So you have invariance of this metric on the multiplication of u by left or by right. So this is an invariance on SU2 to the n of this metric, and that's why it's called bi-invariant. Let's study it for a while. Now I want to study actual motion. I want to study actual motion on this space. What motion? The motion that's generated by a Hamiltonian. U dot IU dot is equal to HU. This is the equation of motion, the time evolution operator. IU dot is H times U. It's also the equation of motion for a state vector, and U could be a state vector, but it's definitely the equation of motion also for unitary operators. I'm going to be interested in converting this to an equation which is independent of H. An equation whose form is independent of H, and therefore it will be true for every H. Remember, I'm interested in an ensemble of H. If I'm interested in an ensemble of H, I would like to write the Schrodinger equation here in a way which doesn't depend on any particular H, and it's pretty easy to do. You first solve for H. Now, this seems like a free lunch, but you solve for H. What is H? H is equal to IU dot, and then multiply from the right by U inverse, U dagger. That gives you H. I just solve this equation. And now differentiate this equation again, IU double dot. 2-time derivatives. That's going to be equal to H times U dot, but now I'm going to plug H in and get that this is equal to I U dot, U dagger, U dot, I think. And this is now an equation of motion, second order instead of first order. The price that I've paid is the equation second order instead of first order. It doesn't depend on the Hamiltonian. This will be true for any Hamiltonian. Did anybody recognize this equation?
So here H is time independent?
Yeah, assuming time is time independent. Yes, absolutely. Time independent.
It's like a rotation order.
It is, yes, but it's connected with something else also.
Why? It doesn't look like H is very time independent. Like, why?
It is.
It
It
is?
is, yes, this is the equation of motion for a time independent Hamiltonian. Anything I do with it will be for a time.
Yeah.
Yeah. It doesn't look like it, but it is. Yeah. But in this form, it's true for any time independent Hamiltonian. Okay. I'll just remind you of an equation. D second x mu by d tau squared or something is equal to some gamma x dot x dot. X dot squared here, what's this equation here?
Geodesic.
That's a question for geodesic. This has two X dots, the U's are coordinates on the space, of course, so that the U's can be are the coordinates. And here's a U dot, and something which doesn't depend on dot, it's gamma. This is the geodesic equation of motion on the space.
Sorry, so by solving for A, you are going to phase space effectively because you are doubling the number of degrees of freedom?
Yes, but, right. But, okay, but then what happened to the Hamiltonian? Where did that go? So let me tell you. In other words, what happened to the J's? The J's which parameterize the Hamiltonian, where did they go? So let's see if we can find them. Let's go back to the Schrodinger equation again. The Schrodinger equation for U, U dot is equal to minus I. Now I'm going to write it in the form summation over I, J sub I, sigma sub I. Remember, this is the whole 4 to the k minus 1 elements of the Pauli algebra. The J's are the things which determine which Hamiltonian we're talking about. And good. Let's solve now for the J's. I can solve for the J's by multiplying by sigma and taking a trace. If I multiply by sigma j and take a trace, that will pick out I equals j, and that will give me j sub I is equal to I trace, I think it's sigma I u dot u data. You throw in a sigma, you take the trace, you sigma, you have a u dot here. Well, sorry, there was a u here, wasn't there? It's Schrodinger equation. U dot is equal to h times u, IH times u. This u got moved over to the other side. And this is solving for j's in terms of the motion, if you like. Now let's go to time t equals 0. At time t equals 0, u is the unit operator. So at time t equals 0, this is just this. U dot, here's our space. Here's our space. We're going right to t equals 0 where the unit operator is. U is 0, but u dot, little differential motions. What is this object? This object is the initial velocity along the I direction, capital I direction. Directions in this space are parameterized by the Pauli algebra. Okay. This object over here, J, is the initial velocity from this point here. So we can identify it with the initial velocity along the I direction. And now we see the pattern. We have a dynamical system. Well, we'll see this is a dynamical system in the sense it does have a Hamiltonian. It has an action. Okay. It's a dynamical system, second order, like Newton, with initial conditions that are the only things that remember the Hamiltonian. And we have a statistical ensemble of J's, which means a statistical ensemble of velocities. If the statistical ensemble is Gaussian, then we have a statistical ensemble of velocities. That's called the Maxwell-Boltzmann distribution. Okay? So the ensemble that we're talking about looks pretty standard. Maxwell-Boltzmann velocity distributions, initial conditions, and one last thing, how do we know that this is a canonical system? How do we know it's canonical in the sense that it's a Hamiltonian, action, and so forth? Well, this is just the geodesic equation of motion. The geodesic equation of motion is derived by an action. Let me rewrite, what did I do? The metric. Let me write the metric in the form G, M, N, capital G, M, N. Vxn, Vxn, where x, m, and n are just coordinates on the space. They could be just the components of the unitary operators, just a general set of coordinates. This becomes just a standard old geodesic equation. If this is the geodesic equation, we know that it's simply generated by this action. This is second order formalism. In second order formalism, this is the action for this motion. It has a Hamiltonian, it has an action, it has canonical momenta. Basically, the canonical momenta, at least at t equals 0, the canonical momenta are the j's, the velocities. And so we have a system, and we have an ensemble of initial states. The ensemble of initial states begins with the initial states begin by assuming that u at time t equals 0 is 1. In other words, we're just calculating e to the minus I h t. At t equals 0, it's just a unit operator. We start here, and we start with a velocity distribution, a spray of velocities, only in the directions which are k-local.
But that's not the ensemble you want to compute the entropy of, right?
That's the ensemble that I think that the complexity is the... but remember what's going to happen. Wait. The system factorizes into positions and momenta. We'll work that out. There's a thermal entropy associated with momenta, but there's also a positional entropy. There's a positional entropy as these guys fly out from the center here. They fill up a region, and that region grows with time.
Yeah, isn't the complexity growth here described earlier the second thing? This is positional entropy.
Yeah, the standard computational complexity would be the position.
Right, okay. That's this.
The question is whether the other parts of the entropy are related to complexity, and yes, they are, but in some other way. That's right. So, and basically by energy conservation, the kinetic part of the entropy is just fixed; it stays constant. This thing spreads out. It spreads out into the ambient space here, and
So how do you know how to do the course?
thus far, I'm using a metric in which the things that I say are not true. Not this metric is not the metric that we would identify with complexity.
That was basically what I was going to ask, is
Yeah.
how do you coarse grain this?
Well,
Because you
I think before we coarse grain it, we want to change it.
Yeah.
Before we coarse grain it, we'll introduce little coarse grain cells, but I think before that we want to change it. Okay.
Good question. So you basically u prime and u are canonically conjugate, or
You dotted.
u dot and u are
Essentially, but yes.
But how do you see the is there some commutator that you can compute and you get one? Or?
There is.
Okay.
But what we have to know, where's the Lagrangian? Okay, let's write out the Lagrangian. The Lagrangian is just, here it is. The Lagrangian is just this tau here being random time. All right, so we just have velocities, and it's a constrained problem because the unitaries are constrained to be unitary. But within the constraints, you can work out the canonical momentum and so forth. And of course, canonical momentum conjugate to u, or to any one of the independent components of u, will be a velocity. So this is a more or less ordinary system.
Okay, but I guess my question is that the commutators, the canonical commutators, they don't live in the original Hilbert space. They live in a new Hilbert space, right? Because I mean, you.
Oh, yeah. Well, whoa, okay, wait.
I mean, this is classical.
This is
the Poisson bracket.
This is classical.
If you want to make the Poisson bracket, this is not the same thing as the commutator.
Right. That's
yeah.
This is classical.
Yeah.
Motion of the Right. So, to put it the way I think it should be said, is the quantum complexity is related to the entropy of a classical system with exponentially large numbers of degrees of freedom, and it looks like this is what it is. Okay. Now, one question is whether the motion on this space is chaotic. Okay. The motion on this space, as it's defined, is not chaotic, but it is generically ergodic. Everybody knows the difference between ergodic and chaotic? If somebody knows it, please tell me, because I want to know.
Chaotic means exponentially diverging, and ergodic means
It just
eventually
fills,
everywhere.
it sort of fills space.
Yeah, like a torus is ergodic.
Yeah, so where is the torus, and how do we know that it fills it? That's pretty easy. You take a particular Hamiltonian. First, start with a particular Hamiltonian. Then we can write u in the form e to the minus I h t, t of tau, and that's equal to the sum over some eigenstates I, e to the I minus I, e sub I, t. Okay. Here there are a set, here's a bunch of phases. At time t equals 0, all the phases are at t equals 0. Or all the phases are at 0 angle. As time goes on, they start to move. And they move with different velocities because different energies, different frequencies. Right? They'll move around the circle, and if the quantum system that we're talking about is, let's call it chaotic, that means something about the energy levels. Most important, it means the energy levels are incommensurate. What that means is that if you wait long enough, you will get these dots here being anywheres in any locations to within epsilon, to within high precision, any precision you like. You will fill up the entire torus generated by this set of phases here. The number, how many phases are there? The number of phases is 2 to the n. The number of eigenvalues, the dimensionality of the space is 2 to the k. The number of energy eigenvalues is 2 to the k. So there's a 2 to the k dimensional torus here, embedded in the SU2 to the k. This is just one Hamiltonian. Now we look at all possible Hamiltonians corresponding to all possible initial conditions, and that will fill up something bigger than a torus, but not a lot bigger. Why not a lot bigger? Because the number of parameters in the Hamiltonian is not very big. It's only a polynomial in K, for a Q local system. So this is the basic dynamical system that we're interested in. Should I go on for another? I'll go on for another couple of minutes. Yeah, another couple of minutes. I want to get to the actual interesting setup, which I think this is all really easy. There's nothing that takes hard mathematics here. Okay. Now, I am interested in a different metric on space. I am interested in what we call complexity metric. Complexity metric is the same metric that we've talked about before, which I call relative complexity. Now I'm thinking about relative complexity between two different unitary operators. Given a unitary and given another unitary, the relative complexity between them is the minimum number of gates that it takes to go from one to the other. You'll have to specify some specification of what you mean by gates. Now, I'm not really proposing this as the definition of complexity that we use. I'm using this for inspiration. This is what we ordinarily mean by some sort of computational complexity, the minimal number of gates to get from one thing to another. Let's just explore its properties. First of all, it is right invariant. we'll think of this, at least when U and V are close to each other, we'll think of it as a kind of metric, the minimum number of gates that takes to go from one another to another. Let's explore its invariances. Let's say the following equation. Take any V and write that this is G, 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 W times V. I've done nothing, I multiply on the right by V. And what I see is that UV, the relative complexity of UV and WV is the same as the relative complexity of U and W. And that means that the relative complexity is right invariant. Okay? What about left invariant? So here we have to put the V over here, and let me put in a V inverse as the V. This object over here is not generally the same as this. In fact, it rarely is. It won't generally be. There will always be V's for which it's not. And so we see that this is not a left invariant metric. The thing that you have, it's just not a left invariant metric. There's no reason to think, and good reasons to think not, that I write here. There should be a W here. V? Yeah. W?
Yeah.
W, yeah.
There's another V. V minus 1, V W.
V minus 1 V, yeah. V W, yeah. Okay. Multiplying by the left on V does not preserve the relative complexity. So relative complexity is a metric. It satisfies the rules of what a metric is. It is, it's always positive or zero. And it's zero if and only if the two operators are the same. And it satisfies the triangle inequality. I think we proved that a number of times ago. It satisfies the triangle inequality. So it is a metric. And this I'm basically using as inspiration for saying that it's a right invariant metric, not a left invariant. Right invariant, but not left invariant. There's a whole field of mathematics that studies left invariant metrics. I am the first person to study right invariant metrics. That happened by accident, of course. I didn't know that there's a field in which people study left invariant metrics. Okay.
Can you consider the Hermitian and what is the difference?
None.
Okay.
Well, there is a difference, but right. It's not. No, but think of all the theorems that can now go with my name. Or some of them with your name. Okay, now here is a theorem. Here is a theorem. I'm also going to make one other assumption. I'm going to assume that the metric that we're going to use to explore complexity is a Riemannian metric, just like the left-right symmetric. Here is a theorem about all right invariant metrics. Right invariant Riemannian metrics. But they have the form sum over I and J. Now I and J are the same things, the Pauli algebra, or the algebra that's generated by the fermions of the SYK model, same idea. D omega, I'll tell you what omega is in a minute, I, a tensor in the IJ space, the Pauli space, times D omega J. This is a pretty simple looking thing. There's something called D omega here. There's a matrix or a tensor in the IJ space and another D. All you have to know now is what D is. D omega I is equal to I trace of D U dagger. You can write it in a number of ways. Sigma I U dot. So when you plug this in, You'll have two u dots. It will be a metric quadratic in velocities. The sigmas will appear, but this will be the form. This is the most general right invariant metric, right invariant Riemannian metric, parameterized by a set of coefficients I, which depend on pairs of directions in the 4 to the k dimensional space.
So it's a metric in this subspace.
What's that?
It's a metric in the subspace of 4 to the k and not in the whole.
This is actually a metric in the whole space. I and j run over
Only 4 to the
k.
Okay.
Yeah, this is
4 to the
actually.
4 to the k or 4 to the q.
Hmm?
I mean, I thought the sigma i's were defined with 4 to the q i's, right?
No, yes, 4 to the q. No, 4 to the, no, 4 to the, 4 to, well, that's why k would be called in. It's the whole algebra that you can, or,
Sorry, but the sigma i's, I mean, they are related with the q locality, right?
not yet. No, not now,
okay,
not now,
okay.
not now. In defining a notion of complexity, we're not going to use that.
Okay.
It's going to come up in another way. It's going to come up in another way. Yeah, okay. You could try restricting this to only k local directions. That would be completely the wrong thing to do. You want to punish non-k local directions, which means make the distance between them very large. In complexity geometry, you want to take things very different, of large complexity separation, and make the distance between them large. In what Nielsen does, he basically he uses the unit matrix for here for all k local directions, and just a huge set of matrix for all non-k local directions. Hugely big. Okay? It's overkill. You don't really want to do that. You want to fix these coefficients in some way which conforms to the physics of black holes better, and that doesn't, actually what it misses is the switchback effect. But here's the most general metric. Anybody know what this whole thing is? You know, some of you may know. I know I don't know. For the case of SU2, what system this is? Just a rotator. It's a rigid body. A rigid body would just being the moment of inertia tensor. What SU2 is, the motion on SU2 is motion of a rigid body. Most general rigid body is described by a moment of inertia tensor here. And with I and j running from 1 to 3, by 1 to 3, well, it's 4 minus 1. So this is actually the motion of a rigid body. It helps sometimes to think about it this way. What would these omegas, the omegas be here? Or better yet, the omega by dt, what would they be?
Yeah.
The angular momentum vectors. Or the angular velocity vectors. The angular velocity vectors. The angular momentum vectors contain I times the omega. So these would be the angular velocities, the things that the Euler called the omegas. The Euler, not the Euler angles, just the angular velocity vectors. This would be the moment of inertia tensor, and this would be the action of a rigid rotator. The rigid rotator is a very simple thing if the eyes are all equal to each other. It's a pretty simple thing if 2 of the eyes are equal to each other and the third one is different. And it's really complicated if all 3 eyes are different. And the cases we'll be interested in, it's a huge magnification of the structure with very different eyes. All right.
Sorry, question. Stupid question. Why do you have a u dot inside? I mean,
Where?
you have a u dot. I thought
Here?
that whole formula should be a function of space, not the derivative.
What's that again?
I thought that the whole formula should be just a function of
Du.
No.
There's too many Ds.
Oh, too many Ds, don't move over.
You just mean you.
I think it's just you. It's just you.
Okay.
I wrote down you the first time and said, well, it must be a dot. You're right.
No, no, happy.
There's
Yes.
only a dot here, right. Okay. This is a metric, and it has, well, okay, we're gonna come back to it. It has the right shape and structure if the eyes are correctly chosen to reflect this kind of relative complexity idea that things are very far from each other if it takes many, many steps to get from one to the other. But we'll come back to that, and I'll tell you more about this space. The most interesting thing about this space is if you go to the bi-invariant metric, and you look at the sectional curvatures. Sectional curvatures means the curvatures of two-dimensional surfaces passing through a plane, generated by geodesics, let's say. The sectional curvatures of the original metric are all positive. That means that geodesics starting out in different directions go like that, and to come together. These metrics are typically negatively curved. These net metrics are typically negatively curved, and the implication of that is, with respect to these metrics, that two geodesics starting out with slightly different Hamiltonians, slightly different initial conditions, will depart. So that's the reason for thinking that when you go to the complexity metric, that you'll see behavior looking chaotic. We've already talked about that. We've already talked about how two starting points, if they're close to each other, will track each other, and then the complexity then will drive them apart. So there's good reason to think that any kind of metric that's reflecting complexity of a system, of a chaotic system, will be negatively curved. It's just saying that things tend to depart. And my guess is that is really the real meaning of quantum chaos, that the motion on this kind of chaos space, on this kind of space which measures, not chaos, but which measures relative complexity, exists as a kind of hyperbolic space with positive Lyapunov exponents. Another feature that we'll talk about is the fact that the leading Lyapunov exponent in this dynamical system is the good old beta over 2 pi. So it's another way of thinking about chaos, and we'll talk about it. Good. Okay. Let's go home and, oh, you guys are going, no, you're not. Richard went to the movie.
There we go.